Okay, so now we're moving on to focus on our cornea and lens and their function in focusing light on the retina. But before we can actually understand how the eye functions as a photoreceptor organ, we kind of need to go into the properties of light. So we're going to start with electromagnetic radiation, and this is down here is the electromagnetic spectrum, and it includes all energy waves, starting with radio waves, which are going to be our longest wavelength at 10 to the third meters, to our shortest waves that we have, which are gamma rays at 10 to the negative fifth nanometers. However, what we can perceive as color is somewhere in between, in the middle of this electromagnetic spectrum. And it falls right here. It's a very, very short area with a wavelength range of 400 to 700 nanometers. And this part of the spectrum is what we refer to as the visible light spectrum. So visible light does travel in the form of waves, and its wavelengths can be measured pretty accurately. So when we're talking about light and we're in the form of energy, we usually call these little packets of energy photons. And the photons travel in a wave-like fashion at really, really high speeds, so about 300,000 kilometers per second. We can think of light as a vibration of energy. But visible light, as we just saw, does contain a mixture of wavelengths. So when light passes through a prism, each of the component waves will actually bend at a different degree. And this disperses the beam of light into the visible spectrum, or a band of colors that we can see. So this is why you might see a rainbow appear after it rains, because of the prismatic effects of the tiny water droplets that are in the air. So within the visible spectrum, our red wavelengths are going to be our longest. So they're going to be at the 700 nanometer range of the visible light spectrum. And then they're also going to have the lowest energy. Our violet wavelengths are going to be the shortest wavelength that we have at 400 nanometers, but they're also going to be the most energetic. So what we perceive as color basically is letting us know that the object is absorbing all of the wavelengths except for the color that we perceive. So if we're looking at grass, it's green. That means grass is absorbing all of the visible light wavelengths except for green. So green is actually going to be reflected off of the surface, which is what we perceive grass as being green. When we're talking about things that look white, that means that they reflect all wavelengths of light. And when we're talking about black objects, that means they absorb all wavelengths of light. So light travels in straight lines, and it is blocked by any non-transparent object, so it can't pass directly through it. When light travels in a given medium, the speed is constant, like we just talked about previously. But when light passes from one transparent medium into another, and they have a difference in density, the speed of light that's traveling can change. So light speeds up as it's going to pass through a less dense object, and it slows as it passes through something that's denser. Because the speed changes, we get something called bending or refraction of a light wave. Basically, when it meets the surface of the different medium at an angle rather than a right angle, at any angle other than a right angle. The greater the angle, the greater amount of bending of light that we actually get. So what's shown to you in the image on the right is a straw in a glass of water, and it appears to break at the air-water surface interface. When we're talking about lenses, a lens is a transparent object curved on one or both of its surfaces. And since we have light that hits at a curve, that means that it's at an angle, so it is refractive. If the lens surface is convex, where it's thickest in the center, kind of like a camera lens, the light rays bend so that they converge or intersect to focus at a single point. If the light is from a distant source, the rays are pretty much parallel and the point at which they focus is what we call the focal point. So in general, the more convex the lens, the more the light bends, and the shorter the focal distance, which is the distance between the lens and the focal point. And when we're talking about concave lenses, that just